In the 1960s, the United States developed a monster secretly designed by a small division within Lockheed Martin, known as Skunk Works. The A-12, which would later lead to the Strategic Reconnaissance 71 project, also known as the BLACKBIRD. The plane of dreams, the only aircraft in this world that the faster it goes, the less fuel it consumes. I personally have been lucky enough to see it in person and spend some time admiring it. And as you probably know, the Strategic Reconnaissance 71 is by far my favorite plane. I have several sweatshirts and this is one of them that reference this aircraft. In fact, I have a miniature Strategic Reconnaissance 71 in my backpack, which always goes with me. And you probably already know how incredible this plane was, the capabilities it had. But do you know what the biggest problem with this plane was? Hello, science junkie. I'm Sergio Hidalgo, an aerospace engineer, and in the next few minutes I'm going to explain to you what this big problem with the Strategic Reconnaissance 71 was. I'll explain it to you in just a few minutes. Something that honestly took me months to understand. Let me give you some context. I've always been passionate about everything related to supersonic fluids and so on. Those of you who have known me for a while already know this very well. And above all, also the topic of air intake in supersonic aircraft engines. When an aircraft flies supersonic, it must slow the air so it enters the engine at subsonic speeds. We already talked about all of this in the video I'm leaving for you in the corner, which is the previous video. For example, the Mikoyan Gurevich 21 uses a system with a cone at the engine intake that moves forward and backward to optimize the process of air intake into the engine. The Concorde, on the other hand, did it with a system of variable ramps that moved to optimize the process of air intake into the engine. And of course, the Strategic Reconnaissance 71, as according to
you probably already
know, also has the cone system that moves forward and backward, making it so that right at cruising speed at Mach 3.2, the shockwave would adapt in the engine nacelle. And in turn, making the internal geometry optimal for compressing the air through shockwaves. Up to this point, everything is normal, everything is fine. We've all seen videos on YouTube where they explain the Strategic Reconnaissance 71D's air intake and how incredible it was. Perfect, but suddenly, one day I came across this video a few months ago.
If the programming in that duct, in that bridge, gets messed up and the shock wave moves out of the duct where the engine expands, it immediately loses 70% of its thrust.
And calm down, let me translate what he means because it's something else. What he's telling us is that the engine at the air intake, right after going through the whole shockwave process, has a small air leak. So you have control over exactly how much air is actually entering the engine. So it could happen that if you take out less air than necessary, even by milliseconds, the shockwave inside the engine would come out, it would be pushed outward, and the engine would lose about 70% of its thrust. When this happened to one of the Strategic Reconnaissance 71's two engines, it would instantly stop producing 70% of its thrust. So, all the force on one side of the Strategic Reconnaissance 71 would suddenly vanish. Therefore, thrust was only being generated by the other engine, the one that was still operating under normal conditions. That force, acting away from the center of gravity, would create a yawing moment, which caused the plane to make a violent turn, and actually, at Mach 3, this could be catastrophic. When I saw this video, I thought, this can't be. I need to understand what's going on. Why is this really happening? And I started searching the internet to find out what this phenomenon was. And I only found videos of former Strategic Reconnaissance 71 pilots telling you how incredible the engine was. And every now and then they would briefly mention this phenomenon, but they left it very vague. They didn't go into any detail at all. And as you already know, I like to understand things from the physics, from the basics, from the very bottom, so I got to work. After searching for weeks, I couldn't find a single interesting document. Suddenly, I came across a paper and a document from Lockheed Martin, both super interesting. The paper is private and I can't show images from it in the video. I was able to access it with a student license. But don't worry, because the Lockheed Martin document is public, and I'm going to explain everything I learned from the paper using the Lockheed Martin document. So let's get to it. There are several important things you need to understand before we go into the explanation given by Lockheed Martin. The first thing you need to understand is what pressure recovery means. Seriously, this term is all over the document. What it's telling us is that when air has a certain speed, we could slow that air down and convert all that energy, which is in the form of speed, into pressure. That's really what commercial airplane engines do. For example, a Boeing 767 that flies at a speed of Mach 0.8. Well, when the air enters the airplane's engine, there's a small diffuser that slows the air down a bit and therefore increases the pressure. That increase in pressure from slowing the air is called pressure recovery. But, of course, here we connect it to what we talked about before, because if a plane is flying at Mach 2, it has to slow the air down a lot. Therefore, the fluid pressure is going to increase tremendously. Therefore, the higher your speed, the greater the pressure recovery can be. If we wanted to represent it on a graph where the vertical axis is pressure recovery, the higher up, the more optimal we would have made the process. We would have obtained higher pressure from the air by slowing it down a bit at the intake. If on this same graph on the x-axis, we put the amount of air entering the engine, we would get a graph like the one Lockheed Martin is showing us in the document. This graph is the key to everything. To understand it, we must focus on several engine parts. The first is at the intake, where the cone that moves is located. Then we have the section where air can enter, the small duct through which air can come in. And then we have the most important part, the air that, as I told you at the beginning, is expelled out of the engine. When I saw diagrams of supersonic engines like the Concords or Strategic Reconnaissance 71s, I noticed some air is removed before entering the engine. I never understood why until I started investigating. It's fundamental, and all supersonic planes with variable geometry have to have these air outlets. Both the cone that moves back and forth, the thickness of the duct through which the air can pass, and the amount of air that is then expelled. These three things are fundamental for the optimal operation of the Strategic Reconnaissance 71's engine. As the Blackbird accelerates past Mach 2, the retractable cone starts to move backward, making the intake area larger and larger. Because if you notice, as the cone moves backward, more and more air is allowed into the engine. Additionally, this movement completely changes the internal geometry the air passes through. And if you notice, there's a point where the area is minimal, a sort of throat, just like with nozzles. When we talked about nozzles, it's exactly the same, just like when we talked about nozzles. If the throat is too small, the air isn't allowed to pass through, and it would get blocked. It's exactly the same as what happened with nozzles when we operated an afterburner. If you remember when we operated the afterburner, the area has to increase, because if not, the flow gets blocked and goes back into the engine. It's exactly the same thing that's happening here. If the throat area of that duct is small enough, it's too small. The air isn't allowed through, and literally the air doesn't go in and out, and that's how the shock wave is generated. And this is known in English as a start the engine, or having half the engine and start it, having the engine not restarted. Honestly, I'm not sure about the literal translation, like I said. This is one reason air stops entering the Strategic Reconnaissance 71 engine's air intake. But also there's another factor that comes into play, and these are the doors that allow air to exit the engine. What this does is control the pressure after the shock wave, after the last shock wave. If the doors were closed and the pressure was too high, the shock wave would tend to move forward, outward, because the pressure, being so high, would push the shock wave outward. So using sensors, when it was detected that the pressure was too high, these doors would open a little to let the air out. And as the air was released, the pressure would drop, therefore the shockwave could return to its original position. Without these doors, the engine would keep restarting every time there was even the slightest disturbance, because it would operate perfectly under design conditions, but in real life, you're not always operating under design conditions. A small disturbance in the air temperature, or a slight sudden movement of the plane, or anything like that would cause the engine to restart, and the shock wave would move outward and stop air from entering the engine. So, the engine doors, rarely discussed, were actually among the Strategic Reconnaissance 71's most important features. Now that you understand, I can show you the chart that Lockheed Martin shows us, which actually graphs the process, this one of Unstart the engine. And I'm gonna tell you how it was solved, how they made the air go back into the engine. On the y-axis, pressure recovery is represented. Remember, the higher the pressure recovery, the better. The x-axis shows the mass flow rate, which is the air entering the engine. The design conditions are 0.1, that is, we assume that Blackbird is operating under ideal conditions. But suddenly a small disturbance could move the shockwave forward, outward. When this happens, the gates would have to open a little and allow air to escape to make the shockwave return to its initial position. Of course, when the doors open a little, they're letting air out, so you're moving a little to the left. Since the mass flow rate, the amount of air entering the engine is decreasing, but we reach a point that would be the limit. One more small disturbance and it would make the engine restart. That's why an engine always needs to have a small margin from 0.1 to 0.2. As I mentioned before, this prevents any disturbance from restarting the engine. But instead, you could open the doors a little and put the shockwave back in the optimal position. Otherwise, you would go straight from 0.2 to 0.3. If you look at the pressure recovery, it has dropped like crazy, but not only the pressure recovery, you've also moved to the left. Therefore, the amount of air entering the engine has also dropped a lot. So once we have the inlet unstarted, once we have the shockwave outside the engine, we need to restart the flow. How do we do this? To do this, extend the cone as much as possible. You also open the doors as much as possible so that the flow can circulate again through the entire engine inlet. When normal airflow returns, the cone retracts. Therefore, the amount of air entering the engine increases, and like I was saying, when you move the cone back, the amount of air coming in increases. But not only that, you're also closing the doors inside the engine. Currently, the engine is receiving the maximum amount of air. You're at 0.6, and when all the shockwaves are in the design position, you go from 0.6 to 0.1, which is the design point. It's honestly insane. This whole process, when the engine detects that the shockwave is outside, that it's unstarted, it moves the cone forward, then back, and closes the gates when airflow normalizes. It's honestly insane. The plane did this automatically when it detected this was happening, but the pilot also had the option to control the gates. I've simplified this so the idea is clear. But actually, the engine didn't just have some gates. It had a first gate behind the shockwave, behind the last shockwave, and then right before entering the turbojet engine, that is, right before the first rotor. It had other small exit holes which could indeed be controlled by the pilot, and he, depending on how he felt the plane was operating, could let more air out or let less air out. After some years, they designed a system to counteract this sudden spin that occurred in the plane because of having the engine restarted. And as soon as it was detected, the moment it was detected that the shockwave had moved outward, the other engine would shut down completely. This way, there wouldn't be a thrust difference between engines, so the plane wouldn't spin. You'd just lose thrust and start to fall. But since the strategic reconnaissance 71 flew so high, in the end it wasn't very important since you could restart both engines and there was no problem. The plane was constantly measuring with sensors how it was doing, at what Mach number it was flying, at what angle of attack, how much crosswind it was getting. It was measuring everything that could be measured, and that way it knew how it had to operate. Based on this, it was known how the cone had to be positioned, and depending on the position of the cone, it was known how the doors had to be. But in addition, the pressure is measured to make sure there is no error. The computer actually, through its calculations, knows what the pressure is going to be, but it's still measured to make sure there's no error. The pressure that the computer has calculated should be there and the actual pressure are compared, and with that small error, adjustments are made. And that's how, in the end, the process becomes completely optimal and the cone is placed in the right position. Well, Science Junkie, I believe this video has been very illustrative and I've explained a process that is actually quite complicated to understand and explain. I had to immerse myself in these documents on my own. No one helped me understand them. If you really like this video, support it. Give it a big like, share it with those who might be interested in the topic. I think it's something nobody talks about on the internet, this bad thing about the Strategic Reconnaissance 71, and it's important to know about it. As I mentioned, all supersonic planes with variable area, like the Concorde, also had this air outlet. So whenever you see that a supersonic engine has the ability to release air from the engine, even before it goes in, it's to prevent the engine from restarting and avoid a shockwave. Right at the front, I would like you to give me a like on this video, which really took a lot of effort for me. If you knew about the phenomenon, or if you didn't before but now do, please leave it down below, because honestly it would make me really happy. And by the way, what was I saying about the sweatshirts? I'm going to release these designs so you can buy them. Since many of you have told me that you would like to have a sweatshirt like this, well, I'm going to release them. From the sweatshirts that I have, I'm going to release 10 of each model, only 10 models, so that there will only be 10 sweatshirts available of the official Science Junkies. So that's it. I'll leave the links below. If you like this topic, I'll leave all the references below, and I really encourage you to read them because it's super interesting. If you have some knowledge about fluid mechanics, aerodynamics, or things like that, I strongly recommend that you read it, because I've really simplified it a lot here. If this is your first time visiting this channel, I recommend that you subscribe down below, because there are some awesome videos coming this year. Seriously, you know, if you want to contact me, you can do it through Instagram or LinkedIn. Subscribe to this channel. By the way, thank you so much to those of you who are supporting me on Patreon and through the channel membership option. Seriously? It has helped me a lot, even if you think it hasn't. It's a small contribution, but it has helped me a lot. As always, you can watch this video here, always above all. Ciencia Blog.